Okay, hi everyone. I am proving proof 2.5, which says that all linear continuous functionals are bounded and vice versa. So the first step of this proof is to show that if we have a linear functional that is continuous at some point x naught, then it's actually continuous everywhere. So what we do to prove this is that we first construct some sequence x sub n, which converges to some choice of x in our domain. And we note that the sequence x sub n minus x plus x naught converges to x naught. And so using this fact that we know that we have a continuous function when we are going towards x naught in the domain, we can kind of create this sequence in the codomain. And then, it's no problem for us at all to add a real number on both sides of that because, if we add a constant to a sequence, we just get the convergence of that sequence plus the constant. But then, of course, since this function f is continuous, we can actually kind of take the arguments and just put them all together, and we end up getting f of x sub n converges to f of x by linearity. And so we've shown that if we have a function, a linear bounded function that is continuous at one point, it's actually continuous at everywhere by the properties of linearity. The second part of this proof is to show that if we have a linear and bounded functional f, that this implies it's continuous. So we're going to show that if we have a sequence x sub n that's converging to the 0 vector, that means that its norm is converging to 0. So now we know by the definition of boundedness, we have this here, that f of its argument is less than some real number m times the norm of that argument. So if we have the x sub n is converging to the 0 vector, we then know that f of x sub n is converging to 0 by the fact that this norm of x sub n is approaching 0. And so we have here that in this case the limit of f of x sub n is equal to f by the limit of x sub n. And so it's continuous at the 0 vector, and by part A, which I just showed, it's therefore continuous everywhere. The final part of this proof is to assume that we have a continuous function and to show that it is bounded. So by definition of continuity, if I choose some epsilon, which is equal to 1, I can find some value of delta such that my x, any x that lies within delta of the 0 vector, implies that this holds. And now because I have this linear functional, I can also scale this up. So I can just multiply this by 1 over delta. And I do the same thing here in the argument, and I can pull that out because it's linear, and then I can do that on both sides. And so what I end up getting is that f of x is less than 1 over delta times the norm of x, and this is actually the definition of boundedness, where m is being played by the role of 1 over delta. So that is proof 2.5.